This section we look at alternating series, and we have a test for convergence here too. If all of our a sub n's are greater than 0, then if we have an alternating series of the following form, that will converge if two things are met. The limit of the terms has to approach 0, and a sub n plus 1 always has to be less than or equal to a sub n for all n. That is, the sequence of terms must be decreasing. So we want to look and see, does this series converge? It is an alternating series, so we're going to check those two conditions. Condition 1, we have to look at the limit of the rule part that isn't the alternating piece. We essentially ignore this for the test. Limit as n goes to infinity of 1 over n does equal 0. Second condition, a sub n plus 1 equals 1 over n plus 1. The question is that less than or equal to 1 over n, our a sub n term, for all n? And that's true. We have 1 over a number that's slightly bigger than 1 over our number, so this has to be smaller. So, by the alternating series test, our series converges. Second example, does this converge? Well, ideally what we want to do at this point is write this so that we have an alternating term. Sorry, I was looking at the wrong problem. So for this one, we have this alternating piece that we're going to ignore. We're going to look at criteria 1, limit as n goes to infinity of n plus 1 over n, that equals 1. So the alternate series test tells us nothing. But if we look at the nth term test, we know that this diverges. But the alternating series test doesn't do us any good for this one. Now, we can use a theorem that will allow us to get an approximation of the sum of a series for an alternating series. If a convergent alternating series is decreasing, that's what that inequality means, then the absolute value of our remainder, r sub n, involved in approximating the sum by s sub n, the nth partial sum, will always be less than or equal to the first neglected term. So if I'm adding up, I'm using the 8th partial sum to approximate our sum. The remainder, the stuff that we didn't add on, will always be less than or equal to that next term, the 9th term, if we're using the 8th partial sum. And a quick proof of this, we're going to assume that our terms are decreasing, and then our remainder is given by the sum minus the nth partial sum. And that would be our alternating series rule minus the sum from 1 to n of the rule. And if I write out terms and write what I'm left with, I get this progression of terms, starting with the n plus first term, the n plus second, the n plus third. And I believe these powers are off by just a little bit. This should be n plus 2, because n plus 1 is what I'm plugging in. This would be n plus 3, n plus 4. But either way, we can factor out negative 1 to the n, and we'll get a nice alternating series. This would be, if I factor out negative 1 to the n, I have negative 1 squared, which is positive, then negative 1 cubed, which is negative, negative 1 to the fourth positive, and so on. So this is our remainder. And I have, if I'm looking at the absolute value of the remainder, that negative 1 to the n goes away. And I have this alternating series. And I can group this together. And what I see is that I have a sub n plus 1 minus a positive number minus another positive number. So that is always going to end up being less than or equal to that next a sub n term. Now let's use this. We're going to approximate the sum of this infinite alternating series by using its first 6 terms. And this is going to converge because of the alternating series test. And why don't you go ahead and check those 2 criteria right now and make sure that you get that it does converge. These are the 2 things that we need to check, and the limit is equal to 0, and the n plus 1 term will always be less than the nth term. So I'm going to write down s sub 6. I want to find that. I get 1 minus 1/2 plus 1/6 minus 1/24 plus 1 over 120 minus 1 over 720. And that is equal to 91 over 144, or approximately 0.63194. Now, knowing that, my remainder, the absolute value of it, will be less than or equal to the 7th term, the next term, 1 over 5040, which is approximately 0.0002. So our sum will be in between that 6th partial sum plus the remainder and that 6th partial sum minus our remainder. And I can add on more terms to get narrowed down even more to find a better approximation for this sum. There's something called absolute convergence. If the absolute value of a series converges, then the original series will also converge. A sub n is called absolutely convergent if the series of the absolute value terms converges. A sub n is called conditionally convergent if the series converges, but the absolute value of our series does not. So here is an example, and this is equal to, if I write this out for a few terms, sine of 1 over 1 plus sine of 2 over 2 plus sine of 3 over 3 and so on. And I'm completely looking at the wrong problem in my notes. Let's start this over again. I suppose it helps to read. So the terms for this are negative 1 over square root of 1 plus 1 over square root 2 minus 1 over square root of 3 plus so on and so on. I'm going to use the alternating series test and see what happens, because this clearly is an alternating series. The limit as n goes to infinity of 1 over square root n, that is definitely 0. That's criteria 1. Criteria 2 is that 1 over square root n plus 1 needs to be less than or equal to 1 over square root n, and that is true. So this series converges, but it doesn't converge absolutely, because the sum, the series represented by 1 over square root of n, which is the absolute value of this rule, is a divergent p-series. So our rule converges conditionally. The next rule that we have is this one, quite complex. If we look at the terms, we have negative 1/3 minus 1/9 plus 1/27 plus 1 over 81 minus so on. This is not alternating. It goes minus, minus, plus, plus. That's not a true alternating series. The alternating series test does not apply here. But what we can do is we can look at the absolute value of this. So since the absolute value of that converges, our series absolutely converges absolutely. And here are the problems associated with this assignment.